This is the Amp Hour Podcast. Recorded March 9th, 2016. Episode 290. An interview with Mark Morin of Newfern.
Welcome to the Amp Hour. I'm Dave Jones from the EEV blog.
And I'm Chris Gamble of Contextual Electronics.
And I'm Mark Morin, Principal Engineer at Newfern.
Welcome, Mark.
You were going to call yourself Jedi Master.
Yeah, I thought he was going to be.
Yeah.
I gave you guys the slip on that one.
I guess we're not going to edit in the lightsaber noise now. Sorry, man.
That's okay.
Hey, Mark, thanks for joining us.
Oh, no problem. Thank you, guys.
So, what is Newfern?
We're a fiber optic company in Connecticut, in the United States. I'm sure like you guys have an international audience,
right, yeah.
so
that's good.
So we make actual fiber. We have an on-site draw. Make the best specialty fibers in the world. If you go to any lab anywhere, there'll be Newfern spools in it. And then we also have a smaller group that makes lasers, and we have manufacturing lasers for like material processing, and then there's higher power lasers that are kind of an ITAR thing. And
what's an ITAR thing for those who don't know?
International Trafficking on Arms Regulation. That means that we're not going to talk about them.
He can't tell you, Dave, because
he can't tell you.
You're not American.
Yeah, past that, we're not talking about it. That's what that means.
That's okay. I'm sure that lasers on their own, or lasers of all types, are interesting. So we don't need to dive into the ITAR stuff.
And everyone wants to hear about lasers, of course, but poor old fiber optic doesn't get much love, does it? And it probably should. There's a lot of tech which goes into fiber, I'm led to believe.
Yes. Tons, I hear.
Tell us.
I'm certainly not involved in that on a day-to-day basis at all. So, they have, I guess they start with a preform, and if anybody here listens to this, I'm going to get butchered for my simplistic explanation, but they start with a glass preform,
there's clear cables. That's about it.
Basically, yeah. And then they put it in this flaming tower, and it just kind of drips down and turns into fiber.
Oh, really? That's cool.
Yeah, it's super simplistic explanation, I suppose.
Yeah,
but what makes your stuff better than the rest? You said like the best optical labs in the world will have your fiber.
Yeah. Well,
what makes it better? Is it lower? I don't know. Is it lower jitter? Is it lower blah blah
super
insert?
pure?
I don't know.
I think our polarization maintaining fiber is one of the fibers everybody stands on.
Right, so that's a key. That's a key parameter. Is it polarization of the light as it travels?
If you're trying to maintain it, it's a huge thing. So there's kind of like if you imagine a flag on top of every photon. And the flags,
I like that.
Right?
Yeah.
And the flags,
that's novel, yeah.
As the photons are going down the pipe, that is the fiber optic, the flags are all randomly oriented. So if you take this polarizing fiber and you coil it up correctly, you can get all the flags to kind of orient themselves over into the same direction over a length of fiber, right? That's what like a polarization
And please
fiber
don't
does.
tell me that makes your audio system sound better.
No,
Excellent.
that certainly does not. I've built the lasers. I could measure the polarization. I couldn't explain to you what they actually do with the polarized light when it comes out of the laser. It's
That's what the scientists are for, right? It's a big deal to the scientists who are doing fiber optic research and stuff like that, right?
Some communications applications I've heard, and then I kind of move on to the next project before any of the implementation's actually done. So
I'm really interested in, it feels, I already know it's not true before it comes out of my mouth, but it feels like fiber's kind of solved, you know what I mean? Because obviously we're talking to Dave right now, and even we're talking to each other, from across the states.
Over fiber, yeah.
So, some of that stuff feels solved, but obviously there's going to be increase in technology. So, even on both the laser side and the fiber side, what is this current state of technology. Even I honestly have no idea.
Oh God, neither do I. The fiber we're talking over, that's the internet, is like SMF-28. It's like a standard telecom long distance communication fiber, and that's like the polarization maintaining fiber I was talking about is a specialty thing for
science experiments and stuff like that.
Some kind of laser that would be a point to point thing, or
well, that's the thing I was going to ask. Like, people talk about just lay fiber and that's it. It's done. Then we'll be able to use the bandwidth of it for the next 100 years.
Kind of.
Is it like but. You're saying it's kind of like a standard kind of, fiber that they lay down. Is that good enough for the traffic, or will they have to rip up all these international fiber links in 10 years because we've got all this electronics and optics? Yeah, like we can't. It's will they find it's not good enough? Maybe in 10, 20 years.
I think for telecom communications, they try and exploit bandwidth that they're not currently using. So if you have the standard EDFA for telecom is a 1550 central wavelength. So you would try and make some kind of out-of-band laser, whether it's ytterbium or thulium, and then you would use those bands to try.
You can't just throw those words in there.
Also, can you spell them? Because I'm taking notes here, and I have no idea what you just said.
Yeah, if you go way down to the bottom of the table of elements, there's a couple of biums. They end in bium, and they're all the rare earth elements that they kind of dope the center of the fiber with, right? So when you pump the fiber with a wavelength in the 960 range, so you shoot that into the cladding of the fiber, right? That's like the outer layer.
So it's in the cladding. It's not in the glass itself.
The elements in the glass it's all glass, but the element is in the center of the glass, and then you kind of shoot a wavelength like 960. The pump light, right? You're trying to pump up the inversion level of the rare earth element atom. So you shoot in 960, for example, and then the index refraction of each layer of the fiber kind of keeps the reflected waves, right? Because the wave is never really going to enter perfectly meridional to the fiber. So
I have experience in that.
I'm going to take a quick break here, guys, and just say I have no idea what you're talking about. I don't expect to, and I just wanted to show some solidarity with some of our listeners right now who are just staring at their podcast player saying, what the hell?
This is great.
So a meridional ray is a ray of like a photon that goes directly down the middle of the fiber. It's like a theoretical perfection that never really gets achieved, right? A skew ray is more at the angle tangent to the side of the fiber. So you launch down some non-zero angle into the core of the fiber, and then it would bounce around in there, right? Between the walls of the fiber.
And then there's losses and stuff like that because of the bouncing, or what?
Because of the bouncing, and if you turn the fiber, your losses increase because the angle of incidence is higher.
Yes.
But the fiber is constructed so that the outer layers are more reflective concentrically as you get to the middle, and then so if you launch light in, it kind of finds its way to the core, right?
Right.
So with like a ytterbium or erbium fiber, so the core is doped with this rare earth element, and you shoot photons into the cladding, and then that finds its way to the core. And then when those photons hit the electron that's actually hanging in the valence layer, the outer valence layer of the rare earth element, it'll knock it up one valence layer, right?
Okay.
And then
because those things have a lot of layers too. Like the stuff at the bottom of the periodic table has tons and tons and tons and tons of
there's hundreds of electrons in these things, right?
Yeah.
Right.
So you bump a couple of electrons up, and when they're at a higher energy state, they either can fall on their own, which is called ASE, automatic stimulated emission, or you can seed them with a signal. So if you shoot a second set of photons that are the exact same wavelength of the rare earth elements natural emission down the fiber, you'll just happen to knock down these electrons and produce clones of the photon you sent in at the same wavelength, right? So
and this all has to happen immediately. Is that?
It's all
like they're chasing each other almostly. I mean, like at the speed of light kind of thing. Or
yes, literally.
Yeah.
So, ytterbium is 1064 would be your central wavelength target for a ytterbium laser. So, you shoot a 1064 photon down the center of a ytterbium doped fiber that's already pumped up, and then every photon that you hit with a photon that you seeded will knock down, or every electron you hit, I should say. When that knocks down a valence layer, it releases, 5 or 10 photons. So the amplification happens there, like on a particle by particle basis.
Wow.
So just over the law of large numbers, because you're just pumping a ton of photons into this fiber, you will hit a bunch of other electrons and emit a ton of photons. So that's kind of how the amplification works. So your laser, like a fiber laser, is just a couple of coils of these things arranged in series, kind of like a circuit. And each bank would have its own pump light that would pump up the rare earth element to a higher, the electrons to a higher valence level. And then because your previous state already has the amplified light coming through, you can pump more electrons up in the sequential states, right? So each stage can have more gain than the last because you're seeding with more photons. So that's basically how the fiber laser works. And then at the end, you put it into some useful, either focus it on a material or focus it into a fiber to send a signal. Your seed photons could be a digital pulse, right?
Yeah.
Some carrier wave, and then you just let your signal ride on that.
So you're talking about basically doing this. This is in a gain stage that's all outside of like a actual transmission piece of fiber, right? So just to simplify, so if I'm sending a signal I'm just sending a single pulse from me to Dave over the transatlantic cable, and I know there's a lot of stuff in between there. But if I'm sending a single pulse, I would use this kind of coil of this ytterbium stuff at the 1064. And then that would basically act as an amplifier. Is that right?
Yes. Well, yeah. So, like, in a simpler version of this is your hometown's fiber network. On some telephone poles, there's going to be a box with a little amplification stage in it. That's just going to crank up the signal enough for the 100 homes that are around that box, and then the line, you go down to the next neighborhood, there's another box that just cranks the signal up again.
All right.
So they kind of daisy chain them around. The transatlantic, I think there's repeaters in the middle.
Yeah, I think there is too, yeah.
Oh, yeah, every
but
100,
the long
50
haul,
Ks, 100 Ks or something, isn't it?
Yeah, and the long haul fiber, though, is like passive, I'm pretty sure.
Right.
Okay.
Now, you mentioned it literally happens at the speed of light, but isn't there a fiber optic latency?
There is some.
Right.
It's
not how much?
Instead of air kind of thing, or what?
Order of magnitude.
There's
is it like Can you give us a rule of thumb figure?
That's I'm gonna guess that it's like tenths or single percentages delay.
Right.
Of the speed of light. It's not half the speed of light or anything like that.
Right. Got it.
And I'm pretty sure that depends on the material in the core.
Absolutely. Yes.
So you'd have to pick which fiber you're talking about, and then you could figure that out. We should have a follow-up episode and actually have one of the optical scientists come on here.
Right.
But basically, when you're going from an electrical to an optical like that, you're saying that there's going to be a laser, and then there's going to be an amplification stage, possibly, and then it's just photons all the way down till you get to a receiver kind of thing.
Well, you could have a laser on its own that's not really high speed, like an internet signal would be different, but just a laser. You could just pump the medium and get the ASE signal and then amplify that, or use some gratings to set up there's like gratings are basically mirrors that are tuned to a wavelength that are inserted in the fiber. So you could use gratings to set up the wavelength you want in a small cavity, small coil, and then you could send that signal down the fiber to a higher amplification stage.
Isn't Oh, sorry, go on.
And that's you'd call it a CW laser, right? Continuous wave.
Right.
If you wanted to send packets of like internet, you would have some kind of diode that you would modulate super fast.
Yeah.
And usually they just dither that diode's intensity by a couple hundred milliamps, I want to say.
Oh, really? They don't take it all the way
no, it doesn't. It never goes to zero.
Yeah.
Right.
If you,
I guess you want to keep it biased, right? So that would make sense.
Right, and the diode, like LEDs and laser diodes, have a threshold where they start emitting. So there's, you'll get to 600 milliamps and there'll be no light, and then at 700 you have a bunch of light. So you could really even just dither around that lasing threshold, but there's spiking involved with that, and I think real companies would just go well into the lasing and then kind of move around and make a 1 this many dB and a 0 is below this dB, right?
Right. Yeah, because then you can test if it's just broken instead of off for a split second kind of thing, right?
Right, exactly.
That's interesting because I figure that a lot of people out there would think that lasers just, on, off, it'd be ones and zeros down here, but it's more analogy than that.
Like everything's analog.
Yay!
Damn
it's all digital on paper and then analog when you try and do it in real life.
Now, isn't the holy grail of fiber optics to have completely optical amplifiers? Like optical charge pumps or whatever the term is, so that you don't have to, in these repeaters you've been talking about, you don't have to convert it to convert optical to a signal and then convert that back to optical again.
Right. I would think that they do that in these repeaters.
Right.
I would think that they just take the fiber in, have an amplification stage that just runs, and then they take the fiber out. That's
a purely optical amplifier because you don't want to have to convert from optical if you don't have to.
You don't want to convert the signal.
No.
From optical to electrical. You'll have to make the pump light with electrical, I would guess, unless there's some really wacky thing they can do. But yeah, I wouldn't think that in just like a long haul amplifier that you would convert from signal to electrical and then back to signal.
Now, do you have any experience in this? Because I used to work at a company where the holy grail of... I used to work in the seismic industry, which is underwater sonar, searching for oil and submarines and other things. The holy grail of that, and everyone... It was always, it's a decade away, is using fiber optics as vibration sensing elements. Have you heard about that or been involved in that?
Now, if you go on our applications page...
there you go.
Click on
Wait, you said you're an engineer, not a salesperson. Come on.
Yeah, well, hey, I'll take it where I can get it.
Yeah, that's right.
But you go on geophysical, and then there's downhole instrumentation, and there's oil and gas production monitoring. And
there it is, geophysical, yep.
So we're 10 years later then, it sounds like.
Oil and gas, yep.
It's probably been 10 years since you were saying that.
So how does that work?
I'm pretty sure they can sense the temperature and vibration down the fiber.
Oh, I didn't know about the temperature. That's interesting.
I know the temperature.
Okay.
That's on like one of our little sales brochures in the lobby. That's for sure. Let's see if I can.
How does it sense that? Just like how the medium changes or something like that?
I think they put another rare earth element or dopant in the center of the fiber, and that has it'd be like having a resistor that you built with a purposely high, a thermistor, right? A high temperature coefficient.
Yep.
So you'd have kind of the same. It's not resistance, but it's you'd have
coefficient.
Index or refraction or coefficient that would. And then I'd assume you'd shoot pulses down, reflect them, and see what you got back for intensity and delay to kind of figure this stuff out.
Yeah.
Now, I'm looking at your list here of your like geophysical products, fiber type products, and there's a category list. And the category list has, like, one of them has the element YB, which I won't try and pronounce.
Ytterbium.
That's the ytterbium.
Yeah.
Ytterbium, right?
Tricky old Y sounding like an I.
but then it's got other categories like 1.0 micron, or it's got select cutoff. Like, what are these categories about?
Well, like 1 micron is the wavelength for a CO2 laser. So if you had a gas laser and then you wanted to launch that into a fiber, you would buy like a 1 micron fiber, I think.
Got it.
So I'm going to take a little step back here.
Yeah, sure.
How the hell did you get into this?
Well, I was in the high school library one day, and they said laser electro-optic technicians were going to be the highest, the highest demand field in the next 10 years. And I said, well, I'll just go to school for that then.
Wait, this was mid to late 90s, is that right?
1996,
yep,
I think.
Exactly, when all the fiber stuff was getting rolled out. Yeah.
Sure.
Yeah.
So, and they happened to have a major at our local community college that was, laser electro-optics. So I just decided I'd enroll in that, and that was the beginning. But I was in a trade school for electronics before that. So, when my high school was a trade school.
Oh, gotcha.
So I already kind of had the electronics bit handled for the most part. So it was a breeze to go through the electronics half of this major was not that much of a challenge, Actually, I think I was able to absorb some of the higher concept classes, like you take a linear circuits class, and there's kids that are still trying to figure out whether what series and parallel means, and they're shoving op amps down your throat a month later, and having the basis from a trade school was actually a big help in kind of figuring that stuff out.
Huge.
So
that's great.
Yep.
So the thing that really strikes me about this already, I mean, obviously this is a very practical application of chemistry, obviously the periodic table, stuff like that, and that is great. Obviously in the electronics field we don't hear about that as much, but like valence electrons matter, right? I mean, it happens in a lot of stuff, but it
happens at the semiconductor physics level,
right? Exactly,
in our industry. But apart from that, no, we don't really. Most application engineers, don't, which is the level we're at.
Would you ever buy like a germanium diode to get the right forward voltage?
Oh yeah, you would.
Like
that's
germanium
about
or silicon is maybe the only time you think about it.
Yeah,
right?
exactly.
That's about it. Yeah.
Yeah, and I mean that's just that's almost like a branding thing as much as anything else. It's like, oh, I need this type instead of I need it because the valence. You have to drop the different energy levels and stuff like that. So, no, it's really cool though, and like that. I've talked to someone. Actually, one of my old bosses, he used to work on really high-speed oscillators, and he was in kind of like the ytterbium type stuff, or maybe it's yttrium. I don't remember at all, but like just those really interesting, exotic type materials that you need to use. But that also drives, of course, the price up and very specialized equipment and everything. So,
yeah, I can imagine.
So, what are you doing So, what are you actually doing there?
Oh, I design the circuit boards that control all this stuff. Basically.
Got it. So he is one of us, folks. He is one of us.
Yeah.
The domain knowledge around the other stuff.
Just because I've been immersed in it for 15 years, I've absorbed all this nonsense.
Right.
But day to day, I'm driving a seat of Altium, and
nice.
or I'm down in the lab actually cobbling together some prototype board to try and prove out whatever we're trying to do that week. For the most part.
So you said there's two different pieces to your business here, right? So there is the actual making of the fiber, but then you said there's like the amplifier side and the stuff that you're building. So what are some of like the device types that you're building at a high level?
So we have a new Q laser, which is a pulsed laser. So if you've bought an 0603 chip resistor, this is the kind of laser that etches the die and then actually scrubs off the carbon resistive element. I've been to
Right.
So
like laser trimming, you're saying? That's what, like the trimming.
Oh, yeah.
Yeah.
I've been to the factory where they do that. It's really neat to watch for about 3 minutes, and then it's incredibly boring for the rest of the time.
Right.
But it's a little ceramic wafer kind of gets vacuumed in onto a tray, and then the laser goes blam, and then everything's kind of etched into a grid, right? Mm-hmm. And then they deposit carbon on it, and then the thing sits there, and like 2 flying lead probes come down and actually measure the resistance while it etches away carbon. It's really neat.
Oh, so it's like that dynamic where it actually is...
Oh, it's unreal how like live it is.
I always assumed it would be like with resistors and stuff like that. It was just a amount of material type thing, or is this for like just the super precise ones?
To be fair, I think those were like 0.01% resistors.
Okay. The stuff that we're paying for out the wazoo anyway. So
right. Yeah. So I think even the 1%ers are just, it etches whatever it etches for 100K, and then it just breaks the wafer up, and they put leads on it, right?
Yeah. That's pretty cool.
And then they sort them afterwards because it's just it's just not worth trimming.
Sure. And then there's applications like metal engraving and etching. If you have a serial number in the side of something, they don't do that with an engraving tool anymore. They just do that with a laser. Huh. Takes zero time.
I've actually seen that. Like if you look at those micro photographs of dyes. Right, you can actually see that there might be some logo or something. It's like obviously been like laser etched into the die rather than chemically etched.
Sure,
because it just looks different. It doesn't look chemically processed. It looks like it's been burned in. With the laser.
And sometimes you can see the dots. It'll almost look like a dot matrix printer.
Mm-hmm. Right.
Put it down. If it's moving really fast, where the laser pulses are coming out at a rate that's comparable to the speed of the actual,
oh wow,
transom or whatever
quick.
they're using.
Right.
Oh, it's a system that uses an XY table, right, where you have a fixed optical piece and then a table that moves around under it. That kind of stuff is not fast enough for that. But there's a device called a galvo that is basically 3 mirrors that move really fast, right? So your scan speed can be millimeters or centimeters per second. That kind of stuff you can get dot resolution out of these lasers.
Wow.
And it actually looks pretty neat. So like we have a test pattern that's a bunch of dots, and they're all arranged in a perfect grid, so you can tell if there's dots off from where they're supposed to be. You can tell that your electronics design is messed up somewhere. Yeah, exactly. Yeah.
And dummy question, but is that
I've got one of those too.
Shoot.
Is that every laser, or is that a specific pulsed?
That's the specific Nu-Q pulsed laser does that.
Okay.
So your operation
because
range.
most people think about like laser is just on. That's it. It's not pulsed. They think it's just on.
Yeah, lasers are meant to kill James Bond, right? That's what they're supposed to use.
Exactly, right. You run it across a table at a spy's crotch.
Slowly, though.
Walk out of the room after you've told him your entire plan, right?
That's right. That's how you haze your interns, is that right?
Yes, exactly.
And follow-up question, why do you pulse the laser?
Oh, the peak power. So if you're like the Nu-Q, for example.
Power, right, yeah.
Right. Your average power is 20, 30, or 50 watts, depending on the model.
Got
right?
it.
But if you're running at a 50 watt at 50 kilohertz, your peak power is
huge.
Kilowatts,
Right.
So the damage threshold of the surface of the material you're attacking is some number, right? And you want to melt it. And if you can just shoot a pulse in a short enough time, it'll just melt the surface or evaporate it. It just goes away.
Oh, I know one thing we can get into. Can
I ask my dumb question first, though?
You can ask your dumb question, then I'll get into it.
So you mentioned the galvos and the mirrors. I've always wondered this. How does a laser bounce off a mirror? I know that's like a really basic question, but why doesn't it etch the mirror? Is it about the focal length or something?
Because the mirror is made of a material that's reflective at the wavelength you're using, hopefully. Or it'll wear out pretty fast, right?
Yeah, you're right, yeah.
The material you're shooting at, like copper at 1064 is very reflective. So if you're trying to etch copper, you have to get a lot more energy. But like aluminum is pretty susceptible, right? So you can
Okay.
etch aluminum very easily.
And what determines that the material's susceptibility to different wavelengths? Then is that just based? Yeah,
that's a whole nother science on its own.
that's another podcast as well. Okay.
Yeah, it's all empirical testing to me, but like I'm sure there's people that can figure that out.
Yeah, that would blow up.
Exactly. Yeah. They're like, hey, this isn't doing anything. I wonder what's going on here, right?
Huh. Okay. No, that's really interesting stuff. I just have no idea where that comes from. So you could have something that just isn't susceptible at a certain wavelength. Like if if like a plastic wasn't susceptible to a certain wavelength, I realize that's probably not the case. But if it wasn't,
no. A silver mirror, for example, like a regular mirror might be silver backed, and silver might not be, absorptive.
Yes, exactly. Absorptive, I guess you say?
If that's a word, at that wavelength. So it might just reflect it. Yep.
So like plywood is a good example, where CO2.
Right.
Like your plywood sheet, that 8x4 sheet you pick up at Home Depot, is cut with a CO2 laser.
Yeah.
In almost every factory. There's no saw cutting this, right? And the CO2 can burn plywood. If you put it under that NuQ laser at 1064, it's not going to do anything. You could run it for an hour and maybe start seeing a spot, but there's not a high damage threshold there.
Right.
Got it. Even though that's a big ass 50-watt kilowatt peak laser, it still wouldn't do anything.
Right.
Yeah.
Yep.
So it matters power plus wavelength.
Right. Yes.
Interesting.
So it's like you have some thermal coefficient of absorption, right? And you get enough heat in the surface and it starts going away, and if you're not absorbing it at a high enough rate, you're just not doing any damage.
Physics for the win.
Sure.
Yep. All right. Laser drivers.
Yeah.
Because there's a lot of electron. It's almost like a black art. Oh, laser drivers. They've got there's special requirements for laser driver circuitry, and I'm guessing you can tell us all about that.
Sure.
Well, something.
Yes. So,
what is the problem? First of all, like everyone I see this on the forum all the time. I'm trying to design this laser driver, but you've got to have super high peak currents. Blah blah blah. Tell us what the issues are.
Well, it depends what you're trying to do. If you wanted to make a, you go online and you find all these like eval boards for laser drivers and.
Mm-hmm.
What is a laser driver? I guess I'm sorry, I don't.
Well, there's laser diodes, right? And you just pump current through it and you get photons out. Is the most basic explanation. It's like a transducer, I suppose you'd say.
So they're current driven devices, just like like
so electrical current turns into photons through this diode,
right?
Yeah,
and there's a bunch of challenges with switching on and off laser diodes. Like when you cross the lasing threshold, you get this relaxation oscillation that makes a little spike, right? So if you just want to shoot a laser diode into a wall, it's really not that complicated. But if you want to start amplifying it in a fiber system, you can't have all these spikes coming out of the laser every time you turn it on and off, right? So you have to have a pretty well under control current source without overshoot or
because it's basically a current source you're switching off and on, and when you switch a current source off and on, you can have issues, especially if it's a large current source.
Yeah, and you're talking on the low end, 10 amps or so, and on the high end, a lot higher.
Yeah, and you've got to switch them fast too.
Well, this is where you get all the problems, right? Everybody can turn one on and
switch.
Leaving it on.
One hertz, right? You switch it with a switch and on off.
We have a 500 millisecond rise time, and it's critically damped, and everything's beautiful. But if you want to, switch at kilohertz or faster, then you have to do a lot of things. And I'm sure you guys understand. We can't drill too deep into this.
Oh, that's okay.
No, we just want generics. Like,
sure.
Do you have to use, is it hard to get special purpose? Do you have to use special purpose transistors to end up doing it? Because,
Not really. It's,
no?
You can use almost a standard DC to DC converter architecture to make your power supply. And, a linear, almost an audio type transistor would give you a
Okay.
You want to have a nice analog region you can control in your transistor, right? You don't want to be just smashing into saturation.
Right.
Yeah.
Depending on your circuit that you have set up to do this, but
Does that mean, well, that would require, like, so if you had, I'm just, like, imagining this in my head, so you have a FET that's switching into a diode like that, and then you're going to want some kind of feedback there. Does that mean you have feedback that's not, that you're using nonlinear feedback then, because you're basically monitoring the diode voltage then? Is that the idea?
Well, you've got to generate a constant current. You've got to remember it's not a,
right. So
it's a constant current generator.
You would use some kind of current feedback loop into your
Okay.
control
Gotcha.
element, right? Whether you're using an op amp or something else. And you would feed the current back and then use your feedback to kind of dampen your signal and hopefully not dampen it so much that your rise time's, useless.
Right.
Yeah.
But at the same time, you have to...
We've replicated a 56K connection on this fiber optic system.
And look, this loop is really stable, but the rise time's half a second, you know. But it's really stable,
Super
it's
stable.
not going to oscillate.
Yep.
Yeah, exactly. And that's fine for some stuff, some guys, some laser sources you just want to turn on and leave on all the time, and that's fine. And then there's some things that you want to go fast, and you have to have really good control over everything. So
That is great. Yeah, that's interesting stuff.
Now, you've been involved in you're doing production and qualification testing and burn-in and stuff like that as well.
So we had this, well, I don't know if you want to lead into this RF design story here.
Yeah,
but
sure.
Why not?
We had
this is an electronics show.
Yes, so which is I kind of wrote this out because I was thinking that this would be electronics focused as we could get here. We had this, well, in the new Q laser, the way you switch it, right, to get a pulse is there's an element called an AOM, which is a acousto-optic modulator. So it's a crystal you put in 150.
Sounds like something the Ghostbusters would use.
That's right.
Something like that, yeah. It's on the proton pack somewhere.
That's right.
And, you put 150 megahertz in it at a couple of watts, and you get a lower optical insertion loss, right? So it's it's kind of like a FET in electronics.
Could you... Wait, optical insertion loss, could you define that too, please?
Right, so you're kind of like a CB radio, like the insertion loss of your cable to your antenna, right?
Gotcha.
It's
like the matching of two things, that kind of thing?
Right. It's like 60 dB when you have no RF going into it, and then the loss goes down to 1 dB when you put a bunch of RF into it. Huh. You get what I'm saying here? So
I think so.
Virtually, if you're putting 10 dB in or 10 dBm in, right, and you have the AOM switched off, you're going to get minus 50 dBm out. And then when you switch the AOM on, you're going to get 9 dBm out.
So it's a matching system. That's the idea. So it effectively...
It's more like a gate, to be honest with you.
Oh, interesting. Okay.
It's stopping photons from flowing through when you don't give it an RF signal.
Oh, interesting.
Right. So that crystal basically controls the entire laser. If that thing shuts off for too long and all your pump diodes are running, all of those fibers will just burn themselves up because they'll have too much energy.
Wow.
Do you ever feel like a wizard where you're like, oh, yes, today I was controlling the crystal, and then I...
If you start explaining it like this, yeah, it sounds like that, but it's...
I put on my robe and my wizard hat.
Day to day, it's a lot simpler than it sounds.
And I walk around with a cane with a big crystal on the end of it.
Sure.
Sorry, we're just super immature and have no idea what you're talking about. So this is what we do when we're confused and scared.
So basically, you drive this thing with a CB radio circuit. Right.
Interesting. Okay.
So it's an old Motorola transistor, an MRF 553, went obsolete in 2012, right? Uh-huh. And we started to try and...
everyone panicked.
Oh, yeah, I'm sure they did. And everybody was at the same time trying to get their last time buys in. And,
right.
We got some, and we immediately started to redesign the board to, find a replacement for this thing, because it's kind of... I don't know if you remember these things. It looks like a cross where there's like 4 leads coming out.
Oh, yes, I know.
And there's a little circular package in the middle.
Yep.
Right?
Yep.
And there's a hole drilled in the board that the thing kind of sits in the pocket.
Uh-huh.
So,
which is a very common package for RF amplifier type chips. You know, if you open up anything, you know, old school RF, you'll find these packages.
Well, it seems like it used to be anyway. But,
it's
you know, there's not a heck of a lot of variety on DigiKey nowadays to find, you know, some replacements that drop in. So we were scouring the internet for a replacement for this thing. We couldn't find anything. We ended up finding one by a fly-by-night obsolete transistor manufacturer, and
we
bought
call
some.
A broker.
Sure. we bought some from one of the big 3 distributors, you know, and tried it out.
Did you buy it in a darkened alley or anything like that? Or
no, you'd be surprised how large of a company was carrying these things.
Okay.
And that's kind of what led credence to the company that was making them, right? So we
this is like a secondhand, like somebody in their garage using an old chip manufacturing equipment.
I think somebody bought the remaining dies from somebody that made these before, right?
Right.
And they just decided we'll crank out as many as we can before the whole thing falls apart. And
I've always said that my retirement plan is to become a chip broker and just find a part like this and then just stockpile them and just charge someone like you through the roof kind of thing.
Buy them at $1.20 and sell them for $10.
Oh,
you know?
More than that. Come on, man.
10?
Yeah, let's stop there.
Well, yeah, the gravy train never ends.
That's right, until it hurts.
So this thing basically passed all of our qualification tests. We did dummy load testing and AOM insertion loss testing, built lasers, ran them for thousands of hours in burn-in, and then we order a reel from this company, like factory direct.
Oh, no. I know what comes next.
So we send those off to our CM, right? And they load them up on a bunch of boards, and we get the boards in, and absolutely nothing works
at all. Yep.
And you're like, what is going on here? We just tested these.
No, you tested the good ones.
Right, exactly. They apparently made like 25 good ones before they made this reel, and so we took one out of the old package we had originally ordered, soldered it onto the board, snaps right on, you know, turns on. So we're all like, this is... If there's any kids out there listening that think
gather around, children.
Electrical engineering is just the gravy train, and it's really a collection of these stomach sinking moments and then a few days of digging yourself out, you know?
Yes.
And so we start going back and forth with them, like, what happened? This is obviously different than the other ones we got, and it took them a while to admit it, but you could see that the package physically changed. The old one had a big fat lead on one side to kind of mark pin 1, and the new one had like a skinny short lead to mark pin 1.
Oh.
So they were like, oh, well, what happened is we bought the remaining dies and packaging, and then like there's no more of those anywhere, and the tooling doesn't exist anymore, so we couldn't make them anymore. So we just started making it with... you know, a newer
whenever
package.
we had light, right?
But it changes the input impedance of the transistor. So the whole circuit is, you'd have to adjust. So he's like, oh yeah, just change some caps and inductors. I'm sure it'll work. And,
this is their blah 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 this RF their, stuff.
Yeah, this is their sales guy on the phone. You know,
right?
And,
well, that's a little better than if the engineer was saying that. I mean, that would be something else. But
yeah, I don't know if they had engineers, to be honest with you.
Oh jeez.
But it was yeah, so we started over from scratch after a year of intermittent work on this. You know?
So who ended up bearing the cost for that?
Oh, I'm pretty sure we ate it.
Right, you just ate it.
What are you going to do, right? I mean, you're dealing with people that, you know...
Don't care.
Yeah, exactly.
Right. They're like, yeah, we sold you the reel. See ya.
Yep.
You know?
That money order didn't come back, you know?
Right, exactly.
You can try and sue them.
Because they weren't guaranteeing specs based on a data sheet, were they? They were just...
Oh, well, the kicker is they said, if you look at the bottom of our data sheet, there's an asterisk that says all specs are subject to change.
Yep.
And
no.
you're, it's a lesson learned. You can't trust anything that's even written down on paper. Right. The other thing is their data sheet didn't have the S parameters in it ever, right?
Right.
So they're like, yeah, it's an unspec feature. That's the most important part of an RF transistor. It's
Can
funny.
you tell us about the S parameters for those out there who aren't conversant with such things?
Right.
In general?
So there's there's an
generic, because you can do an entire course on S parameters.
There's basically an input impedance and then a reflection coefficient and then an output impedance and then like a reflected power coefficient, right? So there's 4 S parameters, S1, S12, S21, and S22.
For any particular device or circuit.
Right. So you'll see this funny looking navigational map in the back of an RF transistor datasheet with a squiggly line drawn on it by some guy, and then he scanned it, right? And that's your... That's
data.
Your
that's data right there.
Yes, that's data.
This is a data sheet, obviously, so there's the
data. Exactly. So
wow.
They're kind of telling you on that map how to match the transistor to the input and output circuit.
Got it.
This is a short version, right?
Yep.
Wow.
That's all we need.
So what happened? So then, okay, so you're a year in, and I think that I'm guessing you guys did great on the procuring enough of the existing ones. That's what happens with last time buys. So you were probably okay for a while.
At this point, we called and begged for a second last time buy.
that never works.
No, it totally worked, Chris. You'd be surprised. We got some, not a full reel. We got a partial.
Right? Okay.
Yeah.
Right.
And then we went to a hole-in-the-wall Southeast Asian distributor that claimed they had some, and we bought a big reel off of them.
Yep.
And then we were testing every piece. Well, we threw some on boards to see if they worked, and it was about a 1 in 10 shot. And we started.
Oh no!
Wow. We started testing.
You didn't selectively test them, did you? You were that desperate.
We started testing. We tested the first 100 off the reel in the lab just to see what the results would be, and it was like 1 out of 10. And we decided to just throw the whole thing in the trash.
Wow!
All right.
And then there was a huge stock of non-roast compliant parts out in the world, right?
Mm-hmm.
It's tempting just to go, look, just nobody mention. Well, just use them.
We'll coat them in silver.
We didn't even talk about that. But there's de-leading services, and we were thinking about buying leaded parts and sending them off to a de-leading service, but it just turned into like, how do you guarantee, we're putting roast compliant on our data sheet, so we can't even mess with it.
Ugh.
So we ended up just probably doing what we should have done in the first place, going to a brand new transistor, working out the whole thing again, and then at the end, the new transistor is a higher bandwidth than the old one, so it amplifies all this junk
which
on
can
our
be
clock.
A problem. Oh yeah, no.
So you end up getting spikes.
All of that crap on your power rail that your old transistor was too slow to
it was
amplify.
Natural
now
filtering.
It's just, it's all coming through, right?
The old one had a roll-off frequency of 175 megahertz, and we're using 150, so it works out perfect. And the new one was, 0 to 500 megahertz, so it amplified all the sideband garbage.
Oh,
and
man.
That makes the resultant laser pulse coming out of the AOM have little spikes in it, so...
So what, you had to put extra filtering in then just to make sure you cleaned everything up and stuff? We
ended up changing the input clock to a pure sine wave crystal oscillator, and that cleaned it up.
Man, that's crazy though. And that is I did very similar work in past jobs as well, and sometimes you're just like, why didn't we just start here,
Yeah.
But, because you didn't want to do any of the work in the beginning, right?
No, exactly. You wanted to see if you could get away with it.
Right. We have real products we want to develop, and not stuff that's already basically done. If we could just find more transistors, so there's no functional reason to get rid of that thing. It was fine. It always worked. So, it was just we couldn't get them anymore. Was the only reason we wanted to change it at all.
Yeah. Also kind of calls out just like how this is not. I don't think it's unique to you guys either. It's just like how dependent we are on. This isn't even single source. I mean, that is single source, but just dependent on the specs of certain types of parts. It's just they're like these linchpin specs, effectively, that we just our products are based on them, and it's scary. It's almost like you have to do like a risk audit around each product and be like, that's the part right there. That's the one that will be screwed from.
Yeah, you could. You get.
You'll never sleep at night, but yeah.
Right. Well, you need a huge staff just to do that.
That's true, yeah.
The other, if you have 1,400 parts on a board, which one are you looking at that they could just change the spec on you and decide that you're done making lasers for a while,
Yeah. And we've joked about this on previous episodes, Chris, but sometimes in a company you'll get promoted to component obsolescence engineer. But it's some big companies that's a real job.
Yeah.
You know, because as you said, like there's hundreds and hundreds of parts, and you know, and with critical specs or whatever, and you know, one of them goes belly up, then yeah.
At the end of the day, a manufacturing company makes their money from making stuff, and if you can't make stuff, you're screwed. So, yeah,
that's the bottom line.
Yeah,
but it's like that project is funny. How many times you go to you're at the top of the mountain. And you crash back down, and then you climb it up again, and then you crash, and it's just like 2 years of basically, you know, intermittent work because you're send a board out to spin, and it takes a while to come back and all that. But, you know, when you get back on it, you're like, oh, yeah, we're totally smoked again. Just, you know, it was deja vu all over again like 4 times. It was pretty funny.
Yeah. So you mentioned 1,400 components on a board. Like, what are some other common? So if someone like Dave cracks open a device that has a laser in it and stuff like that, what are some common circuits that people would see in there? So you were talking here about the diode and the drivers and stuff like that. What else is in there?
Oh, you know what? There's kind of there's a Bob Pease book that I think most of the laser industry used to design most of the lasers. I could link it on your subreddit.
Sure.
But,
yes, please.
Yeah.
It's basically there's a photodiode, transimpedance amplifier.
Okay.
Yeah.
And then there's a current source, right, to drive the laser diode, which would have an op amp as a control system. Maybe not in our particular systems, but I think most lasers you'd open up that you bought off of eBay would have that. There'd certainly be some kind of micro or FPGA in there kind of handling everything.
Yeah. And then like, is it like a ADC as well? I mean, just a...
yeah, well, depending if you have a built-in ADC and DAC in the micro, I guess you could get away without it. But,
oh, I see. Okay. Yeah.
and then, you'd probably have some TTL connector on the front that would control everything.
So this is on like the receiver side, though? That's what we're talking about here? Is like transimpedance amp to actually detect? And
No. That's in your laser, right? You have gain stages, and if one shuts off, your electronics short out, and even like the customer signal goes away, right? To amplify, you have to shut all the laser diodes off before the laser kills itself. So there'd be transimpedance amplifiers monitoring photodiodes at every gain stage to kind of make sure that there's a seed signal coming in before you pump watts and watts in, over, this stuff all happens in hundreds of microseconds time scale. So if you're pumping a couple watts for a couple seconds, it's a game over if there's no input signal.
Yeah.
Because it'll just rail, and then that'll just pump all that junk into the lines and stuff like that.
That energy has to go somewhere.
Right, that ASE term where it like automatic stimulated emission, it just kind of happens, and then once it happens,
overstimulation.
you start bumping those electrons off with random wavelengths in random directions, and then boom, it's all gone. It's over. Especially, yeah.
And what happens if we did that? What would it look like? I mean, does it actually go up in smoke or what?
I bet if you go on YouTube and
I will be doing this,
and we look up self-lased fiber or like plasma ball, you'll see a bunch of videos where there's like a blue plasma ball traveling down the center of a fiber in like a coil, right? So it just like kind of looks like it's going around a racetrack like a sparkler, and it's like
cool.
It sounds like a snake hissing, and you have the evolutionary reaction of that, and like jump out of your shoes, man. It's scary when it happens.
Right.
But luckily, we don't get that often. That's a rarity.
So do you get spec then on like how fast you have to shut stuff down, or is it just kind of like just as fast as possible? I mean,
yeah, that's a thing. That's
like something you would sell to your customers. You'd say we shut down and blah 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 blah.
Well, that's more like a safety feature. Okay. Inside the laser that would manifest itself as like a downtime for the customer, right? So you just be saying like, hey, if something happens, the laser saves itself, and then you cycle power, maybe it recovers on its own, and then the world is right again. Nothing you really want the customer to never notice any of this. It all just happens.
Yeah,
you
right.
know, and
What you could do is just instead you could go cheap on the components and then put a printer on the back, and every time it blows itself up, it prints a coupon for half off the next one. You know?
sure, yeah, that's something.
Yeah, that's marketing genius right there.
Yeah, that's good.
So you mentioned multiple diodes as well. So are those photodiodes you're saying, or are there actual multiple laser diodes?
There's both. For every gain stage in a fiber amplifier, you'd have pump diodes.
And what are those?
It's a laser diode, and it's usually at a wavelength that the rare earth element in the fiber will absorb efficiently, and not necessarily be the wavelength that would transmit down the fiber as data or material processing light, right? So this is off band, I guess you'd call it. And
that's just to juice up the energy in the line? Is that kind of the idea, or what?
Yeah, well, it's providing all of your amplification energy for the laser.
That is so crazy.
It's pretty crazy.
Yeah. And so how do you actually sum all of these together then? So
that's the very highly profitable, patentable optical component that everybody wants to be able to build, right? This, whatever you call it, the combiner, I guess you'd say.
Are there any, patents are public. Are there any public patents we could go look at to figure it out, or no?
Probably.
You're not going to tell them to us.
I've either worked for the company that did it, or we have an NRE with the company that's doing it now, too.
Gotcha.
So I don't want to
Okay, no, that's no problem.
spill too many beans, but...
Well, just to give us an idea, that this is like a separate element outside of the actual circuit board. Is that the idea, or...?
Oh, yeah. So the laser diodes kind of are soldered to the circuit board or wired to the circuit board, depending on the system. Mm-hmm. You pump the current through those. There's a fiber coming out of the laser diode, right? Mm-hmm. There's an optical component inside the laser diode that launches the light out of the die into the fiber, right?
Sure.
And then that fiber splices onto this combiner component, and that there's a bunch of fibers hanging out of one side and one fiber coming out of the other side, right?
Oh,
so you have the one single mode fiber on either side for your signal, right? That's the central fiber you're going down, and then you have all these multi-mode fibers, which is like a larger core, so it's easier to launch the light into. And you would splice your laser diodes onto the multi-mode fibers, and then somewhere in the combiner, all the magic happens where it takes the core light of the multi-mode fibers and puts it into the cladding of the single-mode fiber, so that it can then reflect down to the core where the rare earth element is to turn into amplifying energy, right?
Yeah, that is so cool, though.
It's pretty cool.
Yeah, man,
Can you explain the difference between multi-mode and single mode for those playing along at home?
Well, it depends on the wavelength. There's a number of modes in a fiber. The wavelength is actually spatial. The core size of the fiber can only hold a certain amount of a wave, say. And if your wavelength is a lot shorter than the core of the fiber, then you can have more than one wave in there, right? So if you're multi-moded, it means that if you took this fiber with a red pen laser going down it, right? Mm-hmm. If you had a multi-mode fiber and you shot a red pen laser down it, and then you look at it, the output of the fiber on a piece of paper, right? So you can imagine there's a divergent cone of light coming out of the core of the fiber. You would see 5 spots on the paper because the fiber core is too big for that wavelength. So that's what they call a multi-mode fiber, right? So I guess the larger core diameter fibers are just called multi-mode because they're so big they will have multi-modes in most wavelengths. Yep. And then the smaller ones, you're technically single-moded or maybe just not single-moded, depending on the actual wavelength of the laser you're launching into it.
And from memory, because this was in a galaxy far, far away from me, single-mode fiber had lower loss versus distance.
Yes.
Generally.
Because you're not interfering with your own...
Yeah.
I don't know if it actually interferes or if there's just enough room in there for it to refract.
Because of angles and stuff like that? Is that kind of the idea? How it bounces
You know, we're getting into the territory of fiber where I'm more in generalities than knowing the actual specifics of how
we're masters of hand waving here. So.
I have some experience, but multi-mode, so everyone might be asking, well, why don't you just use single mode all the time? It's because I think the interface is more critical. So if you're trying to, you use that fiber on the back of your PC to connect your audio, whatever the TOS link,
the
whatever it's
SPDIF,
called. I don't know.
Whatever it is.
Yeah, the SPDIF thing, right? That's going to be multi-mode, I believe.
Yes.
Because it's just much easier to align. It's much less critical.
Right.
So.
And you're just trying to launch, like it's audio, so the bandwidth is nothing. And
the distance is meters, tens of meters. It's not 100 kilometers. Yeah.
Right. So you're optimizing for the launch angle of a crappy red LED, right?
Right.
And the core diameter is a lot more critical in like an optical cable than anything else to get as much light as you can.
That's right. That's why we used multi-mode fiber in our seismic cables for data transmission. They'd be 150 meters long, but you've got to join these big cables together in the middle, on the back deck of a boat, tossing around in the middle of the North Sea with all sorts of gunk and crap and everything in there. It's like, you can't exactly get the ideal mate in that you want every time, So, we need like the least critical optical connection we could get. So multi-mode it was,
right?
And we didn't care about loss down like a single 150 meter length where it would be repeated. So
exactly.
So what about? I mean, so like kind of what Dave's talking about here. What about connectors? I mean, so if we're looking at one of the boards that you work on, are there specialized connectors, or is it literally like shoving a piece of fiber into a plastic housing and that does it?
For the most part, no optical connectors on the board. We'd use electrical connectors to go to whatever transducer component. And like the front panel of our laser, is a DB25 and a DB9. Mm-hmm. So it's not, we don't really have, I guess in like telecom, if you were launching the signal down the fiber, you'd probably have either a connector or you'd solder the seed diode right onto the board.
Gotcha. So really you're making boards that then are driving transducers, is that right?
Yeah, or we're reading back the photodiode light from we're reading back some signal tap from a photodiode.
Gotcha. And that also has its own interface and stuff like that.
Right.
Yeah.
And then from that, we make all these decisions on what the laser needs to do at a given moment.
Are there interface problems there at all, or no? Or is it pretty straightforward at that point? Because I imagine these are high frequency signals as well, right?
Somewhat. It's surprisingly low. Everybody looks at an oscilloscope and says, oh, well, when we look at the pulse here, we want to do this. And you're like, well, that's nice if you have an oscilloscope front end on the board to read it with, but that would, be $100 chip at least, right? So, we are manufacturing things and the cost is part of this. So you can't go, your bandwidth of your input circuit is kind of limited by dollars anyway. So you don't really have to do all this ultra high bandwidth. Cabling or anything. But if we had to do something like that, I'd probably just solder right onto the board with the optical component, I think.
But no, it's not. I mean, that's nice that you don't have to even think about that. So, I mean, or not think about that, but it's less of a manufacturing problem for the board then, and more of a system level integration type thing.
Oh yeah, there are fiber connectors. I mean, if you've ever seen these telecom amplifiers, they're covered in them. It's crazy.
I haven't.
Oh, okay. Well,
I'll try and add a link to something. I don't know. Maybe you could send me a link to a generic one after we.
Oh, sure. Yeah.
Like ours, for example, on our seismic cables, we effectively manufactured our own custom optical connector. We would have like a brass ferrule that the two fiber cores, which we would terminate. We'd use a termination machine, and then you'd polish them down. So the fiber itself, the actual glass fiber, would go through a ceramic ferrule, and then you'd actually glue that in there, and then you'd polish, so the fiber's like sticking out of this. Maybe I can get some photos, but the fiber is sticking out of this. Then you'd actually polish it down. So you'd put it in a little jig, and you'd actually polish it on this really fine, sandpaper polishing stuff.
Sure.
And then you'd feed that ceramic thing into a brass ferrule, which would be inside our custom connector, which would have not just the optic, it'd have the all the power cables and all the data cables and everything else in there as well. So it was combined electrical and optical connector, and you join those together, and bang, it just mated the two fibers together, and there'd be a little spring mechanism too that would
like hold them together,
push the two ferrules together. Yeah,
yep, that's cool.
Because because we had to have the spring thing, because otherwise your tolerances would be too tight. You wouldn't be able to match it up every time, and when this thing's waving around in the ocean, lots of stress and strain on it. You want the fiber to take that out, and the two fibers to sort of gently push together all the time. So, so a lot of those things are totally custom like that. So.
There's definitely, that sounds like what they call like an FC connector. If it was just fiber.
It was an FC, yes.
Yeah. Okay.
There was FC. There's FC and SC.
Yes. That's a square one.
Yep.
And then my favorite's the S2000. Which has got like a little doghouse that automatically opens when you connect them.
Oh, yes, yeah.
It's fantastic.
It pops up. So it keeps dust and crap and crud out.
Beautiful, but they're like $400 a piece, so nobody ever wants to use them.
Right, yeah.
But you look at it and you're like, now somebody put some thought into this thing,
So you have a theory that you. One last thing that we want to talk about this, and then one other thing. But what is the theory that you have?
Right. So
you've sent us this before.
We've been talking about this Q1 theory, where the most commonly failed component on everybody's board has to be Q1.
So that's how you actually will just go straight to that, or what?
Yes, and then I'll justify it, right? So you would say, like, why isn't it R1? Or actually, why isn't it Q9, right? Because every board has the annotation starts at 1, right? So Q1 is on every board that has a Q, right?
And it's going to be the transistor that breaks? Is that kind of the thought here?
That's where I'm going, yeah. Like if you're using a discrete transistor, you're usually handling a little more power. If you didn't have that much power, you'd have an opto output or something like that.
Because it'd be the most critical part too. This comes from the design side of things. When you're designing something, you do that critical part first, so it's probably going to be given the designator Q1.
And this is the left to right, up to down annotation does that to you, right? You draw your most critical circuit first, and then you annotate it, and that page has all the low annotations on it. So yes, this is my theory. And then it just it keeps popping up we're like, well, we're going to start annotation at like 11 or something, so we just don't have Q1s anymore, or just keep a tally of our annotation and just. Okay, we used up to 83 on the last board, started 84, just so we never...
Right, a running tally, yeah.
Right, you'll have somebody be like, oh, Q1 failed, and you're like, which... What, like, again? And then it's a totally different system,
Yeah.
All right.
So you get the hairs stand up on the back of your neck every time you hear Q1 after a while.
Yeah, especially if you have to go and replace it with a now obsolete component. You're burning another one, right?
Right, yeah, that's true. And it's never good. But I always thought that it's kind of like they say most accidents are within 2 miles of your home. Mm-hmm. And it's because to go anywhere, you have to drive the first 2 miles. So every time you get in your car, you're driving those 2 miles. It always seemed like a dumb stat to me. And it's the same idea with the Q1 failure. It's like, it's always going to be Q1.
It's statistics, yeah.
Yeah, you'd figure. And like a resistor, there's so many chip resistors on a board that they're automatically going to diffuse themselves. But that's my running theory about the Q1 failure.
I like it. So there's one other thing. Actually, the reason that you and I got in contact with each other, you were mentioning to me about some of the jobs that you guys are hiring for, and I was like, well, you got to tell us about lasers if we're going to talk about the jobs too. So, but you guys are in Connecticut.
We are in Connecticut.
I say as a Clevelander.
So for the if you want to flee the Cleve and come on out here, then we'd be more than happy. to interview you, but I don't know what your statistics for Connecticut or Western New England listeners are, but I figured if there's a few, then it's worth throwing these links out there. We have an opening for an electrical hardware engineer, so you'd be using like Altium to design circuit boards for lasers. If this last conversation has been thrilling to you, by all means, give me a call.
Right.
And,
remember how they haze their new people. Don't forget that.
Right. You will be strapped to a table with a laser pointed at you, so get ready.
Don't worry, you won't absorb it, whatever the frequency
right,
is. So
yes. Well,
the wavelength.
that's the joke, right?
Yeah.
Right.
At the end, you find that out.
Well, where are you guys in Connecticut? I mean, like, where?
So we are 2.5 hours north of New York City, I guess.
Mm-hmm. Okay.
It's the closest big landmark. We're north of Hartford. If you've ever been to Bradley International Airport, we are.
Nope.
We are within. You could throw a snowball and hit Bradley Airport from here. So we're on Route 91, which is like our major highway down here, and anybody from the area will know exactly where I'm talking about. But we're in the town of East Granby. If you just want to go on Google Maps and see how far your commute would be if you applied for this job.
Or how far it would be from New York and Boston.
Right, yes, that too. Yeah, there's clusters of engineering out, in Boston, obviously.
Yeah.
And out here it's a little more sparse. But there's a lot of big defense contractors up on 91 here,
Oh, interesting.
There's a Northrop Grumman and what it used to be Hamilton Sunstrand. I think it's Hamilton something else now. And, I think there's an electric boat down near New Haven.
Yeah, I know that former multiple guests of the show, Greg Charavat, lives down south there now. I'm not sure where. I know he lives on the water somewhere now.
Sure.
But, yeah.
Yeah.
It's interesting. Like, must have been some kind of tech center at some point, right? I mean, because of, like you said, all the defense contracting stuff.
There's a bunch of it. I don't know if it just pops up on every major highway or what, because it's ever present, it seems like.
Yeah, well.
But, yeah, and then we have another opening for an embedded software engineer, So if you
wrong
like writing,
show. Wrong show.
Well,
Yep.
Sorry, guys. Sorry. If anybody wants to make a career change and stop committing all your sins to copper and then just be able to change your switch statement to fix a problem, then you could hop on over to embedded software.
Ain't no obsolete components in embedded software. Right?
No. Yeah.
Well, it sounds cool, man. This is a lot of interesting stuff. I mean, like I said, I have very little knowledge of the whole optical side of things, but it's big. I mean, like there is a lot of need for this stuff.
Yep. And there's a huge amount of science and physics behind it that,
Yeah.
It's certainly interesting
phenomenal
stuff to work on, that's for sure.
Yeah.
Well, thank you very much, Mark, for joining us.
Thank you guys for having me. This is great.
We encourage people to check out the lasers and check out the company. That sounds cool. Thanks, Mark.
Thank you.
Cool. Thanks,
All right,
mate.
have a good one.
Catch you next time.